My name is Khadija Jabbar and my roll number is 37 and I am from the Department of BS Biotechnology. And the topic of my presentation is probing the structure of solids, the process of X-ray crystallography. The presentation layout of my presentation is solid, then properties and structure of solid, X-ray crystallography, working, and then diffraction and interference. And then we will discuss about the probing the structure of solid, Bragg's equation, Nobel Prize holder, and then contribution to chemistry, and then application. Before going to the main topic, we should know about the basic term solids. A solid is the state of matter characterized by particles arranged such that their shape and volume are relatively stable. Fundamental state. A solid is one of the four fundamental states of matter, along with liquid, gases, and plasma. Properties of solids. Properties of solids are definite shape, definite volume, definite melting point, high density, incompressibility, and low rate of diffusion. A solid is characterized by structural rigidity and resistance to a force applied to the surface. Crystalline solids have a long range order to the atom or molecule, and beautiful geometric shapes on the macroscopic scale are a result of specific structure patterns on the atomic and molecular scales. Definition of the X-ray crystallography is the experimental science determining the atomic and molecular structure of a crystal, in which the crystalline structure causes a beam of incident X-rays to diffract into many specific directions. And a point to be noted, the electromagnetic spectrum is made up of all the wavelengths of radiant energy, including visible light, infrared radiation, and microwaves. There is a question arises in the probing the structure of solid X-ray crystallography. How can the structure of a solid be found experimentally? Firstly, we will discuss about the principle of optics. According to a principle of optics, the wavelength of light used to observe an object must be less than twice the length of the object itself. Then the diameter of atom. Since atoms have a diameters of around 2 to 10 raised to power minus 10 milli, and then the visible light detected by our eyes has a wavelength of 4 to 7, 10 raised to power minus 7 m. Explanation. To see atoms, we must use lights with a wavelength of approximately 10 raised to power minus 10 m, which is the X-ray region of the electromagnetic spectrum. Origin of the X-ray crystallography. The origins of the X-ray crystallography go back to the work of Max von Laue in 1912, working on passing X-rays through a crystal of sodium chloride and letting them strike on a photographic plate. Laue noticed that a pattern of spots were produced on the plate, indicating that the X-rays were being diffracted by the atoms in the crystal. A typical diffraction pattern is shown in figure. As you can see, a beam of X-rays impinges on a crystal and strikes on a photographic film, and the rays are diffracted by atoms in the crystal and giving rise to a regular pattern of spots on the film. Atoms within the crystals have spacing of about 10 raised to power 2 picometer, and which corresponds to the wavelength of X-rays. When X-rays interact with the crystalline lattice, a diffraction pattern is formed which reveals the spacing between planes of atoms. So what is diffraction? As shown schematically in figure, diffraction is due to interference between two waves passing through the same region of space at the same time. Diffraction of electromagnetic radiation. It occurs when a beam is scattered by an object containing regularly spaced lines, such as those in a diffraction grating, points such as the atoms in a crystal. This scattering happens only if the spacing between the lines or points is comparable to the wavelength of the radiation. So what is interference? Electromagnetic waves interact with each other. It can be constructive and destructive as well. Explanation. Light passing through two slits separated by a distance similar to the wavelength produce an interference. Destructive interference. If the waves are out of phase, the wave is cancelled and the interference is destructive. If the waves are in phase peak to peak and trough to trough, the combined wave is increased in intensity, and then the interference is constructive. Spots. Constructive interference gives rise to the intense force observed on Low's photographic plate. Destructive interference causes the surrounding light areas. As you can see, constructive interference occurs if the waves are in phase and producing a wave with increased intensity, and destructive interference occurs if the waves are out of phase, resulting in cancellation. X-ray crystallography. There is a question arises, how does the diffraction of X-rays by atoms in a crystal give rise to the observed pattern of spots on a photographic plate? Explanation. In 1913, English physicist William H. Bragg and his 22-year-old son William L. Bragg, the X-rays are diffracted by different layers of atoms in the crystal, leading to constructive interference in some instances but destructive interference in others. Bragg analysis. To understand the Bragg's analysis, consider incoming X-rays with wavelength strike a crystal. Derivation of Bragg's equation. Using trigonometry, you can show that the extra distance BC is equal to the distance between atomic layers d times the sine of the angle. As you can see, sine theta is equal to BC over d, so BC is equal to d sine theta. This figure shows the diffraction of X-ray of wavelength lambda from the atoms in the top two layers of a crystal. If the extra distance is whole number of the wavelengths, the reflected rays are in phase and interfere constructively, making it possible to calculate the distance d between the layers. This is the first layer of atoms and the second layer of atoms, and the incident rays are coming. And the rays striking atoms in the second layer travel a distance equal to the BC plus CV further than rays striking atoms in the first layer. As you can see, and as we can discuss before, if these are the ray 1 and ray 2 are the incident rays, and if the extra distance is a whole number of wavelengths, the reflected rays are in phase and interfere constructively, making it possible to calculate the distance of between the layers. And the path difference is two-way. The extra distance BC is equal to CB must also be traveled again by reflected rays as they exist the crystal, making the total extra distance traveled equal to 2d sine theta. BC plus CB dash is equal to 2d sine theta. The key to Bragg analysis is the realization that the different rays tracking the two layers of atoms are in phase initially but can be in phase after reflection only if the extra distance BC plus CB dash is equal to the whole number of wavelengths n lambda, where n is the integer. If the extra distance is not a whole number of wavelengths, then the reflected rays will be out of phase and will cancel, setting the extra distance 2d sine theta is equal to n lambda, and rearranging to solve the d gives the Bragg's equation. So basically BC plus CB dash is equal to 2d sine theta is equal to n lambda, and Bragg equation is equal to d is equal to n lambda is equal over 2 sine theta. Contribution. For their work, the Bragg shared the 1950 Nobel Prize in Physics. The younger Bragg was 25 years old at the time. For molecular substances, this knowledge of interatomic distances indicates which atoms are close enough to form a bond. X-ray analysis thus provides a means for determining the three-dimensional structure of molecules. This figure shows the computer-generated structure of sucrose as determined by X-ray crystallography. Black is equal to C and red shows the O and white is the H2. A single of crystal sucrose is mounted in an X-ray crystallographing instrument, and then X-ray beam is directed at the crystal and a diffraction pattern is recorded. The pattern of spot is used to determine the geometry of atoms in a molecule, as you can see in this picture. This is the prize contribution, year, laureate, prize, and rationalized. For example, Peter Egger in 2003 get a prize in chemistry by the discovery of water channels. Application of X-ray diffraction. X-ray diffraction has a wide and various application in the chemical, biochemical, physical, material, and mineralogical sciences. First, X-ray method for investigation of drugs, then X-ray method for investigation of textile fibers and polymers, X-ray method for investigation of bones, and then integrated circuits. X-ray, firstly we will discuss about the X-ray method for investigation of drugs. X-ray diffraction has been used for the identification of antibiotic drugs such as B-lactam, tetracyclic, 2-macrolide, antibiotic drug. Each of these drugs has a unique X-ray diffraction pattern that makes their identification possible. Integration circuits. X-ray diffraction has been demonstrated as a method for investigating the complex structure of integrated circuits. X-ray method for investigation of bones. Heating or burning of bones causes recognizable changes in the bone mineral that can be detected using XRD technique, and XRD traces show extreme changes in crystal parameters. X-ray method for investigation of textile fibers and polymers. Forensic examination of any trace evidence is based upon Locard's change principle. Textile fiber are a mixture of crystalline and amorphous substances. It has been reported that X-ray diffraction was used to identify a crystalline deposit which was found on a chair. Advantage of X-ray crystallography include X-ray crystallography provides a two-dimensional view that gives an indication of the three-dimensional structure of a material, relatively cheap and simple, useful for large structures not limited by size or atomic weight, can yield high atomic resolution. Thank you. That's all from my side.